In this video, we will be looking at the first model that we have for this course, which is a linear model, and we will be doing a simple linear regression. Many of you would be familiar with this even from school days and even college days, but we have a slightly different take, though initially it will look very similar. Later on we will see how this fits into the whole machine learning idea. So, please do not be careless with this, because once you understand this idea, a lot of deep learning automatically becomes accessible, because most of the issues that occur in deep learning do occur even in this very simple case. So, it is actually an advantage if you already understand linear regression from before. Okay. So, remember that we were discussing two problems in supervised learning back in the first week. There is classification and there is regression, and we will be looking at regression, which is simply the idea that you have lots of data points and you want to predict, you want to predict y at a particular x which is not yet available. Okay. So, if you have x new, we want to predict the new y. Okay. So, let us take a simple example. This example is about the thermal expansion coefficient. So, the thermal expansion coefficient, as you know, metals expand as you increase the temperature, but this thermal expansion coefficient is actually not a constant, it even varies with temperature. So, here is some data about the thermal expansion coefficient of steel with temperature. This is taken from a source where this thermal expansion coefficient is actually given in Fahrenheit instead of Celsius. Okay. So, you can see a reasonable amount of variation between 6.47 to 2.45 for a large variation in temperature. Remember, this is temperature in Fahrenheit, which is why you get minus 340 etc. In Kelvin you would not get that. Okay. So, the question is, let us say we want, you have all this data in a tabular form and you want the thermal coefficient at some intermediate temperature, let us say at 70 degrees. Okay. So, let us say somewhere here you want. Okay, so, there are several ways of doing it. A very simple way is to simply say I will interpolate, it will be between 50% of this and this. Okay. But suppose you want to use all this data, okay. You do not want to just use the nearby data, you want to use all this data and see if you can come up with a better model. This is usually what happens in data science. We might have one or two data points, but linear interpolation might not always be a good idea. Okay. So, we will see a simple demonstration in MATLAB and see what a regression solution actually looks like for this problem. What you are seeing here is my account in the MATLAB online website. It is accessible to all of you. You are welcome to use the same thing. We will also be sharing a copy of the code that I am showing right now, so that you can try it out for yourself. You are not constrained by this, you can also try the same thing anywhere else in a Jupyter notebook. You will see that the format of what is called the MATLAB live editor is very similar to the Jupyter notebook, if some of you are familiar with Jupyter notebook while using Python. So, I have this example of linear regression for the problem that we just saw on MATLAB. The same data that I showed you is here, it is actually taken from this source, it is actually an excellent source. Okay. So, the source that I am showing here is an excellent source for both data sets as well as general numerical algorithms. I would highly recommend that people who are interested in it can take a look at nm.mathforcollege.com. So, now here is the data. I have coded this up here. This is the MATLAB code. We will be looking at various different ways of doing it as we go on with the course. Once again, you are free to use any programming language that you would like. It is just that as you can see, both for demonstration and for initial testing out, MATLAB is extremely convenient. Okay. So, we look at this, all I have done is coded up this data right here. Okay. I will now execute this code. And now alpha y and t x, which are my x and y coordinates, t is for temperature, alpha is the thermal coefficient, those are now placed. Now, we can look at what the data looks like. You will see now that MATLAB has plotted the data and you see x temperature, y is the coefficient, and there is a slight curve. Okay. Now, we do not know what sort of fit is good for this kind of data. Is it a linear fit which is good? Is it a quadratic fit which is good? Is it a cubic fit which is good? And now it turns out that we can systematically try this out. Okay. I am going to use certain inbuilt MATLAB functions. There are several options for this, especially when we come to later parts of this week. I will tell you what other options exist in MATLAB which are inbuilt functions. We will also be programming this from scratch, because this is a simple thing that we can program from scratch using gradient descent. We will be showing examples for that too. But for now, just to get a physical picture of what is happening, I will just use some inbuilt functions within MATLAB for you to see what it looks like. Okay. So, what we are going to do is what is called polynomial regression. Okay. All that means is I am going to find out, remember, the best fit. If I fit a line for this data, all of us know that the line is not going to fit properly. It is impossible to fit all of these with a single line. Okay. But I could once I try a line, I could try a quadratic curve, I could try a cubic curve, I could try all that for this set of data. Okay. So, we will first try that step by step. There is a function called polynomial fit, polyfit within MATLAB. We are going to try the following 3 equations. Remember, these are now our hypothesis equations. Okay. So, I have written them in exactly the same form that I showed you in the previous video, which is y is w1x plus w0. You can think of this as w0 x bar 0. Okay. So, wn x bar n, that is basically what we are trying. So, this is a linear fit. We will try a linear fit, we will try a quadratic fit, we will try a cubic fit, and the coefficients are stored in these 3 variables: coefficient 1, coefficient 2, coefficient 3. Polyfit simply does the order of polynomial. So, this is a first order polynomial, that is the linear fit is called coef 1, quadratic fit is called coef 2, and cubic fit is called coef 3. So, let us run this too. And you see that some coefficients have come out. Okay. So, the first coefficient, second coefficient, okay, w0, w1, w0, w1, w2, etc. Okay. So, all these are sitting here. Now, but for us, we are visual creatures, we would like to know how good is this fit. Okay. We will run this and we will fit it for this whole thing, and now we see that the linear fit looks like this. It is not unexpected. In some sense, this is what is called the best fit line. Remember, we were trying to find out the optimal W's. So, what polyfit has done is indeed found out this optimal W. It is kind of a fit, whether it is a great fit or not, we will find out. Okay. But remember, suppose I am predicting at 70, I will predict my value somewhere here using this fit, using this hypothesis function that I have just found out. We will now try the quadratic. The quadratic is now the red curve. You will see this fits this much better than the linear. Does it always happen that the quadratic fits better than the linear? We will see later on that this is not necessarily true. Okay. But in this case, it does happen that the quadratic fit was better. Okay. So, it will give a much better prediction for the temperature at the thermal coefficient expansion, thermal coefficient of expansion at 70 degrees. We can now try a cubic fit also, and here is the full data summarized. This line here is the linear fit, the red line is the cubic fit, and the black dotted line, which is almost indistinguishable from the red line, but you will see at the end that the cubic is actually better. Okay. So, for the data set that we were given, we find that the cubic fit looks much nicer than the quadratic fit, and the quadratic fit looks much nicer than the linear fit. Okay. And are looks always important? We will see that that is also not necessarily true in life or in machine learning, so that it is not necessarily a good idea to make something that fits so well. Okay. In this case, it is actually a good idea, but we will see how to formally calculate whether it is a good idea or not later on. Okay. So, we can also calculate our predictions. So, you see different predictions here. The quadratic and the cubic fit about predict about 6.4 into 10 power minus 6, whereas the linear fit, as we saw, predicts much higher, and that is about 6.7 into 10 power minus 6. Okay. So, in the next video we will actually see how these fits work. Okay. We will also see later on in later videos how to use the linear model tool set from MATLAB, but that is not relevant right now, but we will learn how these fits actually work, what is actually going on behind the scenes when we do polyfit or when we do any kind of linear model fit. So, that will be seen in future videos. Thank you.